Now let's take a look at this idea of margin of error. So the margin of error of a statistic is the maximum likely estimation error. We know that there's going to be some sort of error in our estimation, and the margin of error provides us with the maximum likely amount of that error. So it is unlikely that an estimate will differ from the actual value of the population characteristic by more than this margin of error. So let's recall a few properties for the sampling distribution of p hat. So we learned in chapter 8 that the mean is the true proportion. The standard error is the square root of that proportion, 1 minus that proportion over the sample size. And if n is large, p hat sampling distribution will be approximately normal. And so we learned that we were able to approximate the sampling distribution using what we know about the normal distribution. So let's dive into a little bit of the theory real quick so we understand where we're coming from. So go back to chapter 6, where we learned that if a variable has a standard normal distribution, then about 95% of the time, I don't know what I just did there, 95% of the time the value will be between negative 1.96 and 1.96. So if you remember, we did that in chapter 6. We figured out on that standard normal table that to get the middle 95%, we would be looking for z-scores between negative 1.96 and positive 1.96. So for any normal distribution, you would have about 95% of your observed values within approximately 2 standard deviations of the mean, specifically 1.96, but it's about 2. So if n is large, then that p hat sampling distribution will be approximately normal with a mean p and a standard deviation square root of p times 1 minus p over n. So we continue on with some theory. If n is large, then we know that 95% of all possible random samples will produce a value of p hat that is within this 1.96 times the standard deviation of a value. So you can see how we're building on this. So we have a large sample size. We're able to use the normal distribution. We know that 95% of our values are going to fall within 1.96 times the standard deviation, which in this case is given as the square root of p times 1 minus p over n. Also, if n is large, it's unlikely that p hat will be further from these 1.96 standard deviations away from the actual population proportion p. In other words, if n is large, it's unlikely that our p hat will differ by p by more than 1.96 times the standard error of p hat. So we look at that theory, and that helps us develop this process to help us determine the margin of error for our sample proportion when we're using it to estimate our population proportion p. So the things that we need to know is that the sample has to be random. If you didn't take a random sample, then these methods simply don't work. Now, you can relax a little bit on a true simple random sample as long as the sample is selected in a way that is representative of the population. These methods will work. Now, we also learned previously how large is a large enough sample size. And just as a reminder, n times p has to be greater than 10, and n times 1 minus p has to be greater than or equal to 10. So as long as those two conditions are met, then the margin of error is going to be estimated by 1.96 times the square root of p hat times 1 minus p hat over n. Now recognize I did have to use p hats here because the whole point of this is that we don't know p. We're trying to estimate it with p hat, and so we will have to have an estimated margin of error. Now also just note that sometimes that 1.96 is replaced with a 2. Just for simplicity, it's just a little bit neater and easier to multiply, but it won't change the result by a whole lot. So in general, the margin of error is going to be found by taking 1.96 times the standard error. So let's look at a few examples of using those formulas. So if we have a survey of 1,000 adult Americans, the proportion of adults who have less than $1,000 in savings was estimated to be a sample proportion of 0.430. So what's the margin of error? Well, we do 1.96 times our p hat, our 1 minus our p hat, divided by the sample size of this survey, which was 1,000. And so when we multiply that out, we get that this was approximately 0.0307. Now, a note on getting this into your calculator. If you are using a graphing calculator, you should be able to get all of this in there without any problems. But if you're using a scientific calculator, you might want to do everything under the square root first. So I would simplify and see that 0.430 times 1 minus 0.430 divided by 1,000 is 0.0002451, and then take the square root and then multiply that by 1.96. Just make sure you know how to get your calculator to give you this correct answer. Now in example 9.3, we have another survey, 1,534 adults. We found that 89% indicated that they favored expanding solar panel farms in the United States. So how accurate is that estimate? Well, we can answer an accuracy question by finding the margin of error. And our formula for margin of error is 1.96, our p hat, which is 0.89, 1 minus our p hat divided by our sample size, and that's going to give us about 0.157. So that 89% is within about 1.6% of the true proportion of Americans who favor expanding solar panel farms. And so we can see here, based on this particular survey, that there was an overwhelming majority of people favoring the solar panel farm expansion. Now, keep a note that we could have made a mistake. This sample could have been a bad sample. Not because we collected it in a poor way, it just happened to not reflect the population. But this sample leads us to believe that it's a pretty high percentage of people who favor expanding solar panel farms.